Okay, so my name is Roger Gaskell. I'm the CEO of a company called Kognitio, who I bet most of you have never actually heard of. And I'm going to talk to you today about how we run SQL queries in an in-memory database when memory is constrained. And we believe this is an important feature of our product, and we really haven't spoken about it before, but so this is the first time we're going to talk about how it works. I also have with me today Andy McLean, who's our CTO, in case any of you have some deeply technical questions, which I can't answer. So first of all, I'd like to start by talking about what I believe the problem is within memory, and that is that there's never enough memory. Now, I probably need to qualify that a little bit in that there's never enough memory in the space we work in memory, which is big data analytics. Even though over the last few years the density of memory has increased massively and the cost has come down hugely, the data always grows at a rate that's even greater, it's even faster than that. So whereas quite a few years ago when we started out, we were talking about systems with megabytes of memory, hundreds of megabytes, but still megabytes. Now we're really talking about systems with terabytes of memory and tens of terabytes and hundreds of terabytes of memory. So even with that expansion in the size of systems, in all the years I've been in the industry, I've never had any customer or prospect or client say to me, it's fine, I've got plenty of memory. So memory is actually a precious commodity, even today. And as designers and developers of in-memory systems, especially in the big data analytics space, it's beholden on us to actually use it as efficiently as possible. And that's where the query streaming feature that I'm going to talk about today comes in. First of all, I'd just like to give you a bit of background on Kognitio and what we do. I will try and avoid being a product pitch, but I think it's important to explain the background to this feature so you understand where we're coming from and why we needed it. So Kognitio was originally founded in 1988 as a company called Whitecross, and we were founded to develop a database that could be used specifically for decision support. What was then called decision support is now called data analytics. At that time, most databases were designed for transaction processing and performed fairly badly when you tried to do some large-scale data analysis. When we started, there was a new emerging way of writing programs for performance, which was called massively parallel processing, i.e. Splitting a problem up into lots of small parts and executing them all in parallel to make things go faster. So we adopted that as a technology we'd use. We'd split the data up in a shared nothing architecture, and we'd bring lots of parallel processing to bear and allow the analysis of large data sets very quickly. The problem we had was at that time, most systems stored data on slow mechanical spinning disks. And our grand idea of having a massively parallel system was basically scuppered by the fact that we couldn't read data from disk drives fast enough to drive any level of parallelism. So we put 5 or 6 processors in the system, and we'd be waiting on disk I/O, so we might as well add one. So at that point in time, we decided that we would put the data in computer memory. Now, we were fairly young and we were fairly naive, and a lot of people would say in 1988 that was a stupid decision. You know, memory was incredibly expensive, it was fairly rare, but we thought, well, a couple of years' time with progressive technology, it will be realistic for large data sets to be held in memory. And we were right. It just took 20 years longer than we originally anticipated. So a quick intro to the Kognitio technology. It's an in-memory analytical platform. What we primarily do is provide ultra-fast, high-concurrency SQL for big data. And we do it on a number of platforms, which I'll come to. We also have some fairly sophisticated support for embedding non-SQL programs in any language into the product so that we can support advanced analytics, predictive analytics, the sort of stuff that's difficult to do with SQL. And we really specialize in doing high concurrency mixed workloads. So it's where we really are interested in is the high concurrency bit. And this is the key thing that's driven our streaming technology that we're going to talk about. From day one, from 1988 to this day, the architecture has been the same. So massively parallel processing, shared nothing, in memory. We've persisted with that till the point that memory has become cheap enough to put large volumes of data in it. We have several different deployment options. We run on what we call a node, which is basically an industry standard server. We can run on one industry standard server, and we can run on 1,000 industry standard servers or any number in between. They can be a standalone Linux compute cluster, or they could be an existing Hadoop cluster. So if you've already got Hadoop, which is basically a Linux compute cluster, then we can run on that under using the Yarn, which is the Hadoop resource manager. We can do it on-premise, or we can do it in the cloud. So architecturally, we sit here between where the data is what we call persists, where the data lives, and the applications that are using the data. The applications talk to Kognitio. They see us as just another data source, and we are supported as a data source by tools like Tableau and Qlik, MicroStrategy, Microsoft Power BI. And then we pull data from what we call the persistence, which is the storage layer. And the storage layer could be an existing data warehouse. It could be a Hadoop file system. Or in the case of our standalone compute cluster, we can build our own storage layer from the local disk attached to each node. And we turn that into a large, fully fault-tolerant storage array. So it's a fairly flexible, but we are really the middlemen. So the users, we don't interact with users, and we don't really store data unless you're using us in the standalone mode. So when are we used? So we're really designed for large data volumes. Now, a lot of people have a different idea what large data volumes are. So in our case, we generally come into play at about 0.5 terabyte of data. We do smaller. Below 0.5 terabyte, there is plenty of technologies out there, in-memory technologies that work perfectly well. And we go up to about 100 terabytes of active data. And what I mean by active data is the data that's being used for any particular query, as opposed to total data set. We can deal with much larger total data sets. We generally have millions to trillions of records. And we are really using applications where there's a need for speed. So people don't use us unless speed is an issue for them. This can typically be, these days, people trying to do interactive ad hoc analytics using modern visualization tools. They want to click and see something happen. Tools like Qlik, View, Tableau, Power BI, and MicroStrategy, they become very frustrating if when you click something, it takes more than a few seconds to get an answer. So we're really used for that. And we're really used for it in a high query throughput environment. So where you've given those tools to all of your business users as opposed to a few data scientists, and they're all clicking and doing their own reports and analysis, and they're all doing it at different times. And you're getting tens and hundreds of concurrent sessions going on at the same time. And we've tended to be used quite a lot by people who provide data as a service. And by that I mean people who make money from taking some data sets, combining them with some other data sets, providing an interesting app on top, and selling access to it. And their query throughput becomes an important criteria there. So they need something that can put as many queries through as possible. So back to the never enough memory. So what do I mean by never enough memory? Well, we have a fixed amount of memory in any system. And being an in-memory system where we're trying to avoid disk I/O, we've occupied some of that memory for data storage. So this is the data we've loaded into memory, ready to be analyzed. Now, we use in the industry, and we use in Kognitio, lots of techniques to get more into less there. So we have compression, you can columnize and compress, we have tokenize. All these techniques are used to make that as small as possible. But that's not really what I want to talk about today. I want to talk about the more forgotten bit, which is the workspace. In all the years that I have been working in this industry and all the clients I've talked to, I've never come across anybody who's asked us, when they're sizing a system, how much workspace do I need? They generally work on the assumption if they've got 5 terabytes of active data, they need 5 terabytes of memory. And when we say to them, no, you need 7.5 or 10, depending on your concurrency, they seem a bit shocked. So our query streaming is all about how we deal with that workspace. So let's take a simple SQL query. So here we're joining a customer table to an order table. And we're going to then group it by a region and return a count for the number of orders for that particular region and the sum of all the orders. So fairly straightforward SQL query that you see a lot, especially in our space where we do a lot with retail analytics. The query plan for that, or what we call the static query plan, looks something like this. So in this particular example, the data is distributed into memory based on its primary key. So the customer table is distributed on the customer ID, but the order table isn't. So to do this join, we need to do one of two things. We can either replicate the order table, or we can move the order table. Now, replicating the order table is never a particularly good idea if it's bigger than a certain size, because it's a costly operation. And so in this particular scenario, we're going to move the order table so that the data, the rows from the order table are co-located with the rows they need to join to from the customer table. Because bear in mind, this is a distributed system. Each node's got a portion of the data. To do joins, we have to make sure the data is co-located to do the join. So this query plan creates two things in there marked TT1 and TT2. And these are basically temporary tables that we need to create to actually execute this query. And those temporary tables are created and stored in the workspace. So obviously, if we have those temporary tables are going to be large, we have a problem if they overflow workspace. But generally, if the system's sized right, that's not too much a problem. But if we look at the workspace a bit more closely, what tends to happen in a system like ours is we have lots of users doing this at the same time. So the workspace starts to get divided up in between a number of users. So everybody's workspace starts to get smaller, and over time, and more users log on, it becomes more and more fragmented, to the point where what those queries will be doing from a user perspective is returning errors, what we call an out-of-memory error. Sorry, can't execute your query, haven't got enough memory to do it. What then happens is the user retries, or the application retries automatically. So now you've got another session starting, trying the same query again, and the whole thing just builds up and builds up to now you have a system which is effectively ground to a halt and has become unusable to the users. So how much of a problem is this in reality? Well, I can only speak from my experience of talking to customers before we had the query streaming features. And the biggest complaint they had was, we love the speed of your system, but the out-of-memory errors when the system is busy is very frustrating. And what they used to say to us is, we understand that the system is not sized for our peak workload, but we can't size a system for the peak workload. It's just too expensive. So what we would like is it to perform well on our average workload, and when we get a peak load, to still be answered the queries, and we accept that that's slower. Now, in reality, that is actually completely untrue. No user ever accepts something going slower, but it's more desirable than something coming back with what they see as random errors, because they don't know the system's busy. They just, sometimes they run the query, it works, sometimes it doesn't. Very frustrating. So this was a huge problem for us, and this is why we basically developed the query streaming feature. Okay, so what are the possible approaches to fix the problem I just described? Well, we could page to disk when Workspace becomes constrained. It's really a horrible solution for an in-memory system. You've gone into all that effort to put everything in memory and do everything fast, and as soon as it becomes a little bit constrained, you start paging to slow mechanical devices again. The other problem is, when do you page to disk? Do you do it when Workspace becomes low, in which case your performance now drops off a cliff? And if you can imagine you've got tens and hundreds of users happening at the same time, it all starts paging to disk, disk heads start thrashing around, performance becomes absolutely terrible. Or the other choice is you always write Workspace to disk, just in case you start running low, and then you can read it back. Now you've slowed down every query, even if Workspace isn't constrained, because you're writing to disk all the time. In reality, I don't know of any vendor of in-memory data analytics systems that actually uses that approach for all those reasons. The one approach that I do know some people take is the rather simplistic way of dividing the workspace up into a number of chunks, so that you don't get the fragmentation. You have a reasonable amount of workspace for each session, but to do this effectively, you have to limit the concurrency level that you can support, and typically you see numbers like 8. So you can have 8 sessions running concurrently, and after that everything else queues. So besides the concurrency limitations, the other problem with this approach is that it's fairly inefficient use of Workspace, because now you have one session which could be exhausting its workspace and unable to continue, while the other sessions hardly have any of their workspace in use. So for these reasons, Kognitio went for what we call a query streaming approach. And query streaming is an approach where we dynamically allocate workspace as required, on the fly, and we resize as load changes. So we have a system that allocates memory, or buffers as we call them, as queries run. As more queries run, we resize those buffers. They can grow in size, they can reduce in size. It's a very dynamic system. And we have a very fundamental principle that makes all this work, and that's that in an in-memory MPP system, recomputation of the intermediate results is very fast. So we don't take the view that when we've calculated some intermediate results, they're a precious resource that we must protect at all time. We take the view that if workspace is low, we'll just throw away intermediate results and recompute them if we need them or when we need them. The idea behind the system and what it actually achieves is a system that never returns out of memory errors. Now, when I say it tries to achieve that, there are odd occasions. I won't say we guarantee that 100% of the time, but if it does return an out of memory error, then it's a bug as opposed to a limitation of in-memory data analytics. Okay, so Kognitio streaming in a little bit more detail. So here we have the query that we talked about earlier. And as you can see from the top, the customer table is distributed on the customer ID. So we are taking the orders table, we are running a step to redistribute it so that the rows are co-located with the customer table. I should say in that redistribution phase, we're also doing filtering to make sure we only redistribute the data that's required to run that query. And that creates a temporary table, TT1. We then, after that, do the join to the customer table. That creates another temporary table, which is then aggregated up. So each of these steps is running sequentially, one after the other, and it's generating these intermediate temporary result sets. Now, the problem with running the steps one after the other is it's a fairly inefficient use of the resource. Because while a step is blocked, say, waiting for some I/O or some network latency, we're unable to do any other work. So it's not the greatest, most efficient way of running the query. Kognitio query streaming turns the query into something like this. And this happens automatically and dynamically. So our optimizer will create a query plan that looks like the one on the left, and then we will automatically turn it into what we call a streaming query plan. And in a streaming query plan, what we've done is we've turned the temporary table TT1 into a stream, and we'll talk more about that. And we've made all the steps parallel processes that run at the same time, with the data streaming between them. Now, in this particular example is reasonably straightforward because we can simply run the streaming rows from step one past the customer table where they're located. But in the more complicated example where we don't have the customer table distributed on the customer ID, things become a little bit more complicated. Now, this is typical of what happens in an analytical system. So when people load data into memory, they generally can only load it in one particular way. They can distribute it in one way. And most DBAs or users will distribute it based on, they'll have a look at their workload and they'll say this distribution satisfies most of our queries without redistribution of the data. But in an ad hoc environment where you've got lots of users, there will always be queries where that distribution doesn't work. And so we're often in a situation where we're having to redistribute rows around to satisfy queries. So the query plan for this involves both tables being redistributed. So we've got an extra step in here to redistribute the customer table, and we've got an extra temporary table in the place. Now, on the face of it, that doesn't look like a big overhead, but it has huge implications for streaming. Because now we can't simply have the customer table fixed in place and run all the rows from the orders table past it to do the join. Because we might be in a situation where the first row that comes out of the order table stream needs to join to the last row that comes out of the customer table stream. So just running in that way doesn't work. So the way we solve this in Kognitio is we introduce something called a buffered stream. And a buffered stream is a stream, the other streams, by the way, are called pass-through streams. A buffered stream has an extra thing in that what it does as the rows are streaming through is it keeps a history buffer of all the rows that have happened. So we get a query plan that looks more like this. So in this scenario, both the rows from the order table and the rows from the customer table are streaming. The order table is streaming through a pass-through stream, and a pass-through stream means we look at the row and we throw it away. We don't keep it. We use it, we throw it away. A buffered stream means we take the row, we use it, and then we store it in a buffer. And the idea behind a buffer is that we can then use that again. So effectively what's happening here is we're taking chunks of data from the orders table, we're streaming the customer table past that chunk, doing the joins we can do, passing the resultant rows up through to the aggregation, and that aggregation step is doing the aggregation, and all this is happening in parallel. When the next chunk of data comes from the step one stream, we will rerun, instead of rerunning the whole distribution step two, we'll just replay the history buffer so that we can join those rows to the new rows that have come from step one without having to do step two again. Yeah.
So if, let's say, I have an application that has hundreds of tables.
Yeah.
Right. And so who determines, like, at what point in
Yeah, we do. No, we work that out. So that's when we turn the static query plan produced by the optimizer into a dynamic query streaming plan. The system automatically works out the types of streams it needs to use. Right. The important thing here, and those who have, amongst you are quite sharp-eyed and have been following this, is what the history buffer effectively ends up with is just another copy of the data as in TT2, in temporary table 2. So we haven't saved any space, so how does this actually help? Well, it helps because what we allow is the system, when it becomes busy and constrained on Workspace, we allow it to arbitrarily, not arbitrarily, completely the wrong word, we allow it to, without warning, throw away history buffers. So a query can be in the middle of working like I just described, data coming in from step 1 to step 1, the data run past it from step 2, next set of data, the history buffer replayed. In the middle of that process, the system overall, managing the workspace, can say, I'm low on workspace, sorry, you're going to lose your history buffer. Now that comes back to the point I mentioned earlier, which is one of the premises we make here is recompute is cheap in an in-memory system. If that happens, all we do is restart step 2. And we run the step 2 process of filtering and redistributing the data again. Now, obviously this means that the query slows down. But back to my point at the beginning, this was specifically designed to cope with a scenario where the customers told us that we just want, in the situation when we know the system's overloaded, we want it to answer the question. So in this scenario, we can always answer the question, we just might be reiterating around the loops several times. Now, how this looks in a little bit more detail, so step by step. So here we have the order table being redistributed and going into step 3, filling up what we call a join buffer. So data's flowing in, streaming in. Step 2 starts to stream rows from the customer table. And then when we believe we've got enough data in the join buffer, and there's lots of complicated decisions that are made of when that's enough, and lots of heuristics that go into that, we then start passing the data from the customer table past that join buffer and actually doing the join. As soon as we start doing the join, rows start flowing up to step 4 to do the aggregations. At the same time as we are doing that particular join, we're writing the rows that are coming through from streaming through from step 2 to the history buffer. So as once the first join buffer has been joined, we now take the next buffer, which has been filling at the time this has all been going on. So the step 1 data has been coming in chunks into buffers. When each buffer fills, we do the join. So the first join, we're doing it by reading data directly from step 2. The second buffer, we've now got a history buffer with all the rows in from step 2. We just replay against the next block of data. So effectively what's happening, and at the same time as we're doing that, the data coming out of the old history buffer is actually being written into a new history buffer. So as the old history buffer decreases, empties, the new history buffer is filling, which is the diagram at the top there. The question is, what happens when we're in a situation where the system decides it's constrained and we throw away we lose our history buffer? Well, the system simply reverts back to running the data, get the step 2 again. So the rows now come streaming out at a slower rate, and we will again try to fill up a history buffer, so assuming that, because this is an active dynamic system, some memory will become available and we can build the history buffer so we don't have to do that again. If that doesn't actually happen, then we will just keep streaming from step 2. The query will run slower, but it will complete. So in a Kognitio system, when we're doing this, there's actually lots of very complex decisions that are being made all of the time. So we're deciding what size buffers can be. There's lots of balances that are made. For example, we could decide that we make the join buffers bigger, so we have to go around the loop more times. But then we end up with less available workspace, which means there's more chance that we could lose our history buffer. All those sort of decisions the system is having to make and optimize for all of the time. And in fact, what we have is a cost-based decision-making system that's worked out the cost of doing all these things, the cost of redistribution data, the cost of having a bigger buffer. All of these things are taken into account during the analysis of how to manage this whole flow. Now, there's a lot of information actually being used here to make these decisions. And these decisions are all actually about memory management. You're managing memory. So it's very different to the sort of approach of using a cache to do this sort of thing, where actually you've got some fairly crude metrics to decide which blocks you're going to drop. And you don't really know what the effect of stuff that's running when you drop those blocks. Whereas in this system, we have a lot of heuristics around the cost of doing things and trying to work out how to do this. Now, what we have to remember is that this is a fairly, this abstract way of looking at it simplifies the whole thing, because what's actually happening is all of this is running on every node at the same time for hundreds of queries at the same time. So basically, each node is making those decisions individually. So it's deciding what buffers to use. It's deciding when to drop history, deciding when to keep history. And it's also having to manage flow control from other nodes which are sending its data. So there's a lot of stuff going on here. Now, in the early days when we first implemented this, it worked fairly well when data was, when Workspace was reasonably well available, but it degraded very quickly. Workspace became constrained. But we've been doing this for over a decade now, and it's been subjected to a huge amount of real-world applications and has steadily improved. There's been lots of iterations with lots of new features going in, and it's now pretty good at this, and it works pretty well. But it's a complicated thing to implement. Probably the most difficult thing to implement in this environment is how do you avoid deadlocking? So how do you avoid the fact that process A is waiting for process B, which is waiting for process C, which is waiting for process A? You've got probably thousands and tens of thousands of processes here. Many of them are communicating with each other. And I know from talking to other vendors who have thought and considered this, this has been the biggest issue they've had to solve. But it does actually work in a Kognitio system. Every Kognitio system out there today uses query streaming as the way of running queries. The key thing about the query streaming is it's effectively optimized for the situation where there's plenty of workspace. So we're trying not to make a query slower when there's a lot of workspace, just to cope with the situation of this constrained workspace. And we believe query streaming does this. It's optimized for that. If workspace becomes constrained, we will still answer the query given enough time. And that's the base behind it. That was the original design goal of the Kognitio streaming. Okay, so that's really what I tried to do there is give you a flavor of how Kognitio streaming works. in the product. Those of you who understand this sort of stuff will realise, well, how'd they do this, how'd they do that? There's pieces missing there. It's sort of deliberate, and also because I don't know. Unfortunately, I employ people who do. But also, this is one of our key USPs as a product. It's part of our secret sauce. There's very few in-memory systems that work on the basis that we will always, in-memory, answer your query, even if you haven't got enough workspace to do it. We will never give you an out-of-memory error. So it's a key thing for us. So I do apologise, it's not a complete picture, and it just shows you the basics, how it works. But you know, things like how we avoid the deadlocking is very important to us, and lots of other vendors have failed on that point. Finally, I just want to give you an example use case that we have as a customer. So we have many of these. This is a particularly new one to us, and it's where query streaming comes into its own. Inmar are a US company you've probably never heard of, but they're worth $2 billion. And they sit as the middleman between retailers and manufacturers in the US. So I don't know whether you know, in the US, they don't really use loyalty schemes. They tend to use vouchers. The manufacturers issue a voucher. The customer takes it into the retailer and gets some money off some products. Now, the retailer has to claim that money back from the manufacturer, and that's a big, complicated task. So what they do is they just give all of their data to Inmar, and Inmar works out who owes who what. So what they've ended up with, that's their core business. What they've ended up with is billions and billions on trillions of point-of-sale transactions from retailers. And what they wanted to do was see if they could monetize that, because they very cleverly wrote into their contracts that they had the right to use that data. So they decided the way they would do that is build a Hadoop cluster, and hopefully you've all vaguely heard of Hadoop, and store the data on Hadoop, because Hadoop is a cheap way of storing lots of data. What Hadoop is not very good at is allowing you to use that data and interact with it. And what they wanted to do was provide access for customers who paid them, online access to a portal where they could just go on and basically ask any question of the data. So they weren't trying to dictate that you can only answer these questions. They were just saying, here's the data set. You can do all sorts of complex analytics on this data set. And you can do it when you want, and you can do it interactively. And so you have a platform here which could be doing anything at any time. It could have one user on it. It could have 100 users on it. It could have 1,000 users on it at any one particular point in time. They could not, the clients are paying. The clients could not be in a situation where they're doing some analytics and get an out-of-memory error. So the query streaming feature we put in is crucial for this. This application wouldn't be possible without the ability to query stream. You can't have paying clients getting errors all the time when the system's busy. They don't know the system's busy. They don't care the system's busy. When they actually did some testing of what we call Kognitio on Hadoop, so it's our Hadoop version of the product, versus Hive, which is the standard way of interacting with data with SQL on Hadoop, it was roughly 300 times faster for any individual query on the same data. But that's not really the point. I mean, it's important, but the point is not that. The point is what happens when the system becomes busy, and how do you support an interactive workload without any major issues. So hopefully that you found that interesting, and thanks for listening. I do have Andy here, our CTO, so if you do have any deeply technical questions about how this works, because I realise, as I said, there's lots of holes in the description, then Andy will be more than happy to answer them.